Welcome back, everybody. This is our fourth class in NEET previous year questions for chapter Moving Charges and Magnetism of class 12th. Before this video, we have made 3 videos in this series, and all of those videos are available on our YouTube channel in the playlist section. We have also started similar series for JEE mains previous year's questions, so you can find those videos in the playlist section also. And if some of your friends are preparing for JEE, then you can guide them through those videos. Also, if you like these videos, then do press the like button, share them, and subscribe to our channel. And if you want to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, let's start today's video. And today we will be starting from around question 30, I think. This was the last question number 31. Let's move to question number 32. A current loop consists of two identical semicircular parts, each of radius r, one lying in xy plane and another in xz plane. If the current in the loop is I, the resultant magnetic field due to these two semicircular parts at the common center. So let's first draw our axis. And we need a line also. So suppose this is x-axis, this is y-axis, and this is z-axis. Now one plane is in xy plane, one semicircle is in xy plane. So one of our semicircle will look like this, which is in xy plane, and other in xz plane. Second is in xz plane, so second will look like something like this. So this is a complete loop which is bent in such a way that some of its part is in xy plane and some of it is in yz plane, and it has a current I. So suppose this is current I, and we draw a line here. So here we have current I like this, and here we have current I flowing like this. Let mark some point. So A, B, C, and D. So now first of all, we will find magnetic field due to each of the part, as each of these semicircles cover only up to 180-degree angle. So magnetic field due to each semicircle will be mu node I by 2r into 180 by 360. So it will be mu node I by 4 of the r. And now let's find out the direction. So for this semicircle CBA, here current is going from right to the left direction, and using right hand screw rule we can find out that if you direct your thumb towards the left direction, so you will find that magnetic field will be uh, on the lower side will be coming out of the page. So it will be outward direction of the page. So magnetic field due to a CBA part of the loop will be mu node I by 4 of the r into direction will be positive k. So k. Now magnetic field due to the remaining part ADC will be, if we now again apply a right hand screw rule on ADC part of the loop, we will find that magnetic field will be again coming out of the center or out of the plane at the center point. So this will be again mu node I by 4r of k vector. So total magnetic field will be sum of both of these. So it will be B total mu node I by 4r of k plus mu node I by 4r of, wait a minute, oh, we made a mistake. That for ADC, the magnetic field will be outward but in the J direction, because here loop is in XZ plane, so magnetic field will be in the Y direction. So that will be it will be in the J direction. Here, let me explain it again. Our first loop CBA, the first loop is in XY plane, so its magnetic field will be in the Z plane. Second loop ADC is in XZ plane, so magnetic field will be in the Y plane or J plane. Positive, negative, that will be decided according to the direction of the current. But magnetic field is always perpendicular to the loop's plane. So here it will be in the J direction. And now if we find the magnitude, we have to take vector sum. So it will be B total magnitude. It will be mu node I by 4r as common into under root k square plus j square, that is 1 square plus 1 square, that is 2. And we can write it like, it will be, we have mu node I by 2 root 2 of the r, that is option A for us. Now let's move to the next one. Two circular coils 1 and 2 are made of the same wire, but radius of the first coil is twice that of second coil. In what ratio potential difference should be applied across them so that magnetic field at the center is same? So as mentioned, that magnetic field is same, and we have material of the wire is same, but radius is different. So let's first use the condition that magnetic field at their center is same, means B1 is equal to B2, and for a we have assuming these both of the coils have equal number of turns, and we are assuming that they have only one turn. So magnetic field at the center will be mu node I1 by twice of R1 is equal to mu node I2 by twice of R2. So mu node get cancelled, twice get cancelled, and from here I1 by I2 is equal to R1 by R2, and it is mentioned that radius of first coil is twice the second coil, means R1 by R2 is equal to 2. So this will be 2, and from this we will get I1 is equal to twice of I2, means current in the first coil is twice of the current in the second coil. Now as we get to the current and we have to find the potential, means we have to involve the Ohm's law, and according to Ohm's law we know that V is equal to IR, and we have the ratio of current, and we have to find out ratio of potentials. So ratio of potential will be V1 by V2 will be equal to I1 R1 by I2 and R2. We have the ratio of the currents, we have to find out the ratio of the potentials. So now potential, resistance, we have to find out ratio of resistances. Now resistance is given by rho L by A. As they are made of same material, so their resistivity is same. We know that their area, because we know their ratio of radiuses, then we can find ratio of their areas. And now coming to the length, their length can be found out as both of these wires are made of a circular coil. Both of these wires are made of circular coil, means their length will be equal to their circumference. So we can reduce this formula of resistance to R. Length will be equal to circumference, that will be 2 pi R, divided by area will be pi R square. So cancelling, pi get cancelled. So what we have, resistance is equal to 2 rho by R. That will be the formula for resistance. And now using this method, we will have V1 by V2. I1 by I2 is equal to 2, and R1 by R2 will be, as 2 will be same and material is same, so rho is same. So we have here R1 and R2, and we know R2 by R1 is equal to, okay, we made a silly mistake here, and that can be a point of confusion. And that point is, here we have two type of radiuses. Let me explain how. On the side, that first radius is the radius of the coil, that is R1. So this is the radius of the coil, and when we are taking resistance, then that resistance is depends upon the area, and that area depends upon the radius of the wire. So radius of wire is different as compared to radius of the coil, and this is the mistake we made here. As both the wire is identical in both of these cases, so area will stay same. That's the mistake I made here, that I assume that the radius of coil is also same the radius of the wire. So radius of wire is different, which is used for calculating the resistance, and radius of coil is different, which is used to calculate the magnetic field. So here A will stay the same. So let me correct this. So length will be twice pi into the radius of the coil, and area will stay same because it is same wire. So resistance, we can say this is the value of resistance, and or we can say resistance is just proportional to the radius. And here we will get, now this formula will be reversed. So R1 by R2, and that will be R1 by R2, and ratio of R1 and R2 is 2, so it will be 2 into 2, that will be 4. So option C will be the right answer here. Moving to the next one. An electron moves in circular orbit with uniform speed v. It produces magnetic field at the center of the circle. The radius of the circle is proportional to. So we know that radius of a circle given by this formula, mv by qb. So here radius will be proportional to just v by b, but this is the value of the radius when a electron or charge particle moves in external field. This is the value when charge particle moves in external field, but here it is asked, or it is mentioned, that electron is moving with uniform speed in a circular orbit, and that electron is producing the magnetic field. So here we have to find the value of magnetic field produced by the electron, and then we have to find radius out of that, we can say, that formula. So we have to clear this. And now if electron is moving in circular orbit with velocity v and radius suppose r, so its circumference will be 2 pi r, and time period will be 2 pi r by v. And why I am calculating the time period? Because it is not clear that how much rotations electron is taking in a 1 second. And magnetic field, if we have a charge which is taking n rotation per second, then magnetic field in a loop or in a closed ring is given by n mu node I by twice of r. To find this value of n, means number of rotation, we have to find out its frequency, and frequency can be found out using value of time period. So frequency will be 1 by t, that is v by 2 pi r. Now putting this value here, value of magnetic field will be v mu node I by 2 pi r into 2r. And actually we have current here. So yes, current is as a value of current we will put also. Current is charge by time. So charge by time, suppose charge is q and time is 1 second we are taking, so it will be q by t or q by 1. So it will become velocity into nu node into charge. Time is 1, so 4 pi r square. And from here, r square is equal to velocity mu node q by 4 pi into b, and or r square is proportional to v by b, or we can say r is proportional to under root v by b, that is option C. So there is slight difference in the statement, that is changing the whole answer. Let's move to the next one. Magnetic field of a given length of a wire for a single turn coil at the center is B. Then the value for the 2 turns wire. And we have already solved this type of question when we had a we can say we had a loop with magnetic field B, and when we had a coil with n number of turns, and the relation between these two, that magnetic field at the center of the coil was given by n square times magnetic field of the loop, provided length of these two wires are equal, means twice the circumference of this coil loop will be 2 pi into radius of loop is equal to n times 2 pi r radius of the coil. So length of wire should remain constant, current should remain constant in these two conditions. Magnetic field at the center of the coil is n square times magnetic field at the center of the loop. Now moving to the next one. From Ampere's circuit law, for a long straight wire of circular cross section carrying a steady current, the variation of magnetic field is inside and outside of wire is uniform, remain constant in both regions, linearly increasing function of r, and linearly decreasing function of r distance up to boundary of the wire, and then linearly increasing one of the outside. So now for a solid wire, we know that diagram of magnetic field versus distance looks like something like this, that if x-axis represents the distance and y-axis represents the value of magnetic field, so initially magnetic field increases linearly, and after reaching the surface it decreases as 1 by r. So that's the relation, and for that relation we have option C that satisfies this one, and we will also derive this as if you have no idea regarding how this relation arrives. So for that, let us consider a wire. Suppose this is our wire and it has a current I flowing through it, and we want to find magnetic field inside the wire at some distance. So suppose this is center and we are finding magnetic field at x distance from the center. This distance is x. So we know the law that integral b dot dl is equal to mu node I. Now we will find the well, we want to find value of magnetic field at distance x, so we will have bx here, and this dl is the uh, integral of the distance, so we will have circumference here, so that will be 2 pi x and mu naught times the current up to this distance x, and as we know that total current in this wire is I and current is divided by area, so total current is I, per unit current will be pi times r square, where r is the radius, into multiplying the area of this loop, that is pi x square. So x pi get cancelled and x get cancelled, and we can write Bx is equal to mu node I by 2 pi r square into x. So magnetic field is directly proportional to distance, which give us straight line. Now let's find out for a point outside of the wire. For a point outside of the wire, suppose distance is y now. So now this formula will reduce to BDL into mu node I. As now outside of the wire there is no current, only current present inside the wire, so current will remain as it is, and we will have B 2 pi y is equal to mu node I, and from this magnetic field will be mu node I by 2 pi y, or inversely proportional to the distance. So that's how we get this falling curve or decreasing curve. So option C will be the right answer. Moving to the next one. So here a thick current carrying cable radius r carries current I uniformly distributed. The variation of magnetic field due to the cable with the distance r. So we have to find out variation of magnetic field where radius is capital R. So we just solved this question and we just proved that how this graph arrives, and the answer is here is option C will be the right answer. And here it should be capital R. Only then this answer should be the right one. Moving to the next one. A cylindrical conductor of radius r carrying a constant current. The plot of magnitude of magnetic field by the distance d from the center of the conductor is correctly represented by the which of the diagram. So here it is not mentioned that either this cylinder is hollow or filled. Now in case of if cylinder is hollow, then inside the cylinder magnetic field will be 0, and in that regard option A will be the right answer. And if it is completely filled, then we know we just solved it in the previous question, then option B will be the right answer. But mostly if it is hollow, it is mentioned, so we assume that it is a solid cylinder or filled cylinder, so option B will be the right answer here. Moving to the next one. A long straight wire of radius A carries steady current I. The current uniformly distributed over its cross section. The ratio of magnetic field B and B dash at radial distance A by 2 and 2A respectively from the axis. So first we will find magnetic field at A by 2 and then 2A. So for A by 2. So it will be integral B, we mark at as B, into twice 2 pi A by 2 is equal to mu node. Now current has to be divided, as radius is A, so current per unit area is equal to I by pi A square multiply pi A by 2 square means A square by 4. So pi get cancelled, A square get cancelled, here 2 get cancelled, we have B into 2 pi A is equal to sorry, B into pi A is equal to mu node I by 4, and value of B is mu node I by 4 pi A. Now coming to the B dash, where distance is 2A. So B dash into 2 pi into radius, that is 2A, is equal to mu node I. Now current will stay as it is now, because we are outside of the wire, and outside of the wire we don't have additional contribution of the current. So B dash will be mu node I by 4 pi A. And as we can see that both of the values are equal, so their ratio will be 1:1. Option B is the right answer here. Let's move to the next one. So two identical long conductor wires AOB and COD are placed right angled each other with one above other such that O is their common point for the two. The wire carries I1, I2 currents respectively. Point P lying at a distance D from O along a direction perpendicular to the plane of containing wires. The magnetic field at the point P will be. So we have to find magnetic field at point P. So first let's draw the diagram. Suppose this is our first wire and this is our second wire, and these both two are perpendicular to each other. And as mentioned, that point P lying at distance D along the direction perpendicular to the plane of wires. So this is the plane of wire and point P is at perpendicular distance D. So this is our point P and it is perpendicular to the plane of these two wires, containing wires. Now we have to find out direct magnitude of the magnetic field at point P. So suppose this wire is AB and this wire is CD. Now we can take a random direction of current in both of these wires. There are 4 possible configurations, but value of magnetic field, magnitude will stay same in all configuration, only direction will change. And as per question, we have only asked magnitude, so we can choose any direction of the current in the wire. So we will go with the current directions. Now let's find out for the wire AB, it is a long straight conductor. So magnetic field due to this wire at point P will be out of the plane of the paper. This will be out of the plane of the paper, and magnetic field due to CD will be in the downward direction. So these two fields, let me draw point P again. This is point P. We have one field that is out of the plane of paper and one field that is in the downward direction, and their angle is 90 degree. Means if we take their vector sum, they will be added according to the direction. So let's write the value of magnetic fields. So magnetic field due to AB conductor will be mu node I, as these are long straight conductors, so magnetic field will be mu node I by 2 pi d, and due to AB it will be out of the plane, means out of the screen, so we take it as K direction. And magnetic field due to CD will be in the downward direction, so we take it as J, or Y direction, negative Y direction. And if we write the combined field, it will be mu node I by 2 pi d. Also currents are different, I think. Currents are different, so I1 and I2. So I will not be written here. Mu node 2 pi d. I1k minus I2j. That will be the vector field. And if we take the magnitude, it will be mu node twice pi d under root I1 square plus I2 square. So that will be the option D for us. And you can see that direction does not matter in magnitude, so magnitude will stay same whatever the direction of the current we choose. So with this, we end this video here. Hopefully again you will find this video helpful and informative also. If you like this video, then do press the like button, share it, and subscribe to our channel. And also, if you want to donate us something, you can scan any of these QR codes in front of your screen and donate us whatever amount you want. Any amount of help will be highly appreciated. So with this, again, thanks for watching, and we will meet in next video.